All right, today we're diving into what might be one of the most important algorithms ever invented, the fast Fourier transform. And at its heart, it's really all about a clever shortcut, a discovery so powerful it literally shapes the digital world all around us. So let's get into it. Okay, let me start by asking you a question. How would you make a calculation 1,000,000 times faster? Not just a little bit faster, but 1,000,000 times. I mean, it sounds pretty impossible, right? But that's the exact problem that sparked the creation of the algorithm we're talking about today. So to really get why the solution is so brilliant, we've got to understand the problem it was trying to solve. And it was a huge one, a classic computational bottleneck. A point where the math was just so slow that it was holding back entire fields of technology. Right at the center of this whole thing is something called the discrete Fourier transform, or DFT. The best way to think about it is like a mathematical prism. You feed it a complex signal, say a sound wave, and it breaks it down into all of its simple individual frequencies. Super useful stuff. But there's a massive catch when you try to actually compute it. And this is the catch. The simple, obvious way to calculate the DFT has what we call O of n squared complexity. Basically, if you double the amount of data, the calculation time doesn't just double, it quadruples. It gets slow fast. But then you have the fast Fourier transform, the FFT, which gets you the exact same answer, but with O of n log n complexity. And the difference between those two in the real world? Well, it's absolutely staggering. Okay, let's make this real. Imagine a signal with about 1,000,000 data points, which is pretty standard for something like audio. The slow O of n squared way would take over 1,000,000,000,000 operations. 1,000,000,000,000. The fast O of n log n method, just around 21 million. That's not just an improvement. That's the difference between something that's only a theory on a blackboard and a tool you can actually use. It's literally why we can have things like real-time audio processing at all. So how in the world does the FFT pull off this incredible speed up? Well, it's not magic, but it is a really, really clever strategy that we call divide and conquer. The core idea, the aha moment, was noticing a hidden symmetry in the math. The creators of the algorithm realized you could take this one big, gnarly problem and just split the signal into two smaller ones, all the even-numbered parts and all the odd-numbered parts. I know it sounds simple, but that one little split is the key that unlocks the whole thing. So here's the game plan, really. You start with your big problem. You break it into two problems that are half the size. You solve those two smaller problems, and then, and this is the really clever part, you just combine their results to get the final answer. And you do this recursively, just keep splitting and splitting, until the problems become so tiny they're trivial to solve. So let's take a look at how that combination step actually works. Okay, now we're going to go a little deeper. The core operation, the little engine that combines all these smaller results, has a pretty cool nickname. It's called the butterfly. And it's called that because if you draw a diagram of what it's doing, the crisscrossing lines really do look like a butterfly's wings. This little operation is where all the magic happens. You can think of the whole FFT like a recipe with three main ingredients. First, you have to reshuffle your input data in this very specific way called bit reversal. Then, you do those simple butterfly operations we just mentioned. That's the core math. And finally, you multiply by something called twiddle factors. That sounds complicated, but they're really just correction numbers to make sure everything lines up perfectly when you combine the pieces. Okay, so a really common question people ask is, hey, does this trick only work if my signal length is a power of 2, like 1024 or 2048? And for a long time, yeah, that was a big limitation. But then along came something called Bluestein's algorithm, which found this brilliant way to reframe the problem as something called a convolution. You can think of it as a kind of mathematical mixing, and that one trick makes the FFT work for any size input, which is just incredibly useful. All right, so we get it. It's fast, it's clever, but where do you actually run into this thing in the real world? The short answer? Pretty much everywhere. Okay, so anytime you've ever played with an audio equalizer, boosting the bass, cutting the treble, that's an FFT working right there, behind the scenes. It's what separates all the frequencies so you can actually mess with them. Or how about this, when you take a picture and save it as a JPEG file? Yep, a close cousin of the FFT is used to transform all that image data. It helps figure out which details are less important to our eyes, and then it throws them away to make the file size way smaller. Even the way you're watching this right now, 4G, 5G, Wi-Fi, All of these networks rely heavily on the FFT to pack and unpack huge amounts of data onto radio waves. It's completely fundamental to how we communicate today. And here's a classic one for any computer science student or anyone prepping for a tech interview. Turns out, multiplying two really big polynomials is, surprisingly, the exact same kind of problem as convolution. And the FFT, it's the fastest way we know how to do it. All right, let's wrap up by boiling this all down to the absolute must-know takeaways, especially if you're getting ready for an interview or just want the key points to stick. First thing, and this is super important, please get this distinction right. The DFT is the what. It's the mathematical idea of transforming a signal from the time domain to the frequency domain. The FFT is the how. It's the super efficient algorithm we use to actually compute the DFT. They are not the same thing. Here's your cheat sheet on complexity. The naive, straightforward DFT, O of n squared. Just way too slow for anything practical. The FFT, O of n log n. That's the gold standard, what everyone uses. And then there's this other one, the NTT, or number theoretic transform. It's for special cases, like in cryptography, where you need perfect, exact answers with massive numbers and can't afford even tiny rounding errors. And hey, if you really want to nail that interview question, have these 3 points in your back pocket. First, know that the time complexity comes from this recurrence relation. T of n equals 2t n over 2 plus O of n. Second, if they ask about input sizes that aren't a power of 2, you mention Bluestein's algorithm. And third, know how to get back from frequency to time. The inverse FFT is basically the same algorithm. You just flip one sign and divide the whole result by n at the end. And that really brings us to the big idea here. The story of the FFT is all about finding a hidden pattern, a secret structure in a problem that looked impossible, and using it to turn that problem into something totally manageable. And it really makes you wonder, right? What other impossible problems are out there right now, just waiting for someone to find that one clever hidden shortcut?